Hi, this is Miss Dorman, and we're going to talk about inverse functions. So you should have this handout, and you should have tried these problems first. And if you didn't, you should pause the video and go ahead and try this. This first one is saying fill in the table of values for f of x. So you should be looking for a pattern, looking at the outputs that are already given, and figuring out what you do to the inputs to get the outputs. Okay, so I'm going to look at these positive ones first. And I know that 5 times 3 is 15, and that's close to 14. So if I just take 1 away, I get 14. And I'm going to try that for the next one. 6 times 3, that's 18. Take away 1, that's 17. So that works for both of these numbers. I'm going to go over to the negative 4 and the negative 13. Negative 4 times 3 is 12, negative 12. And then I take away 1, I get negative 13. Okay, so that works for all the numbers. So I'm just going to fill in the table with the rest of them, doing the same pattern. So times 3, and then minus 1. So negative 2 times 3, negative 6, and then minus 1, negative 7. 0 times 3 is 0, minus 1. 1 times 3 is 3, minus 1. 2 times 3 is 6, minus 1, 5. 3 times 3 is 9, minus 1. And 10 times 3 is 30, but minus 1 is 29. Okay, so I got my table filled in. Write in words what happens to the input to find f of x. Well, that was basically what I was just saying. Multiply by 3 and subtract 1, and then write an equation for it. So f of x is 3x minus 1. All right, we have another problem like that, but it's saying it's g of x this time. So fill in a table for the values of g of x. Again, if you haven't done this yet, you have a handout. You should be trying it. You're trying to look at the outputs that are given, figure out what to do with the input to get the output. So I know that 8, if I add 1 to that, I get 9, and then divide by 3, I get 3. So once you figure out maybe a way to go from one input to the output, you're seeing if that works for the other number that's given. So I'm going to see if the same thing happens. I multiplied by 3 and subtracted 1. I added 1. I'm going to write it down so I don't forget. Add 1 and then divide by 3. So if I add 1 to 8, I get 9. And then if I divide that by 3, I got 3. If I add 1 to 1, or negative 1, I get 0. And then if I divide that by 3, I get 0. So I added 1 and then divided by 3. It works for both of those values that were given, so I'm going to keep filling in the rest. If I add 1 to negative 13, I get negative 12, and divide by 3, negative 4. Add 1 to negative 7, I get negative 6, and then divide by 3. Add 1 to 2, I get 3, divide by 3. 5 plus 1 is 6, and then divide by 3, I get 2. Pause for a second because I was double checking the last one. 2 plus 1 is 3, divide by 3, yes, okay. 14 plus 1 is 15, and then divide by 3, I get 5. And 17 plus 1 is 18, divide by 3, I get 6. And 29 plus 1 is 30, divide by 3, I get 10. These numbers look really familiar. Write in words what happens to the input to find g of x. So we're just writing in words what I've been saying, add 1 and divide by 3. And then write an equation. So we're taking x, we're adding 1, and then dividing by 3. Okay, so this one was asking, this is on the handout, explain in your own words how these two functions are related to each other. So if we go back to these tables, these numbers when we were filling them in looked really familiar. And that's because these inputs for the first table for f of x, negative 4, negative 2, and so on, were the outputs for g of x. And then the outputs for f of x, negative 13, negative 7, negative 1, and so on, were the inputs for g of x, were the x values, negative 13, negative 7, negative 1. So the tables are just flip-flopped. The values are switched. The x and y values are switched, or the inputs and outputs are switched. So the inputs and outputs for f of x are switched to get g of x. And then if we look at the equations, when we go back again, the first equation for f of x was multiply by 3 and subtract 1. And then for g of x, this should say g of x, it was add 1 and divide by 3. So again, this first one had multiply by 3, subtract 1. The next one has add 1, divide by 3. So those are inverse operations. So I put the operations in g of x are inverses of the operations of f of x. Inverse operations are operations that undo each other. So for example, the inverse of adding is subtracting. The inverse of multiplying is dividing. The inverse of taking the square root, so you have the square root of x. The inverse of that would be squaring x. So they're operations that just, I don't know what happened there. The operations just undo each other and you get the value that you started with. So if you added 5, you get a number, and then you subtract 5, you go back to where you started. The next problem is saying let's just graph. You can just graph all the points in each of the tables, or you can take the functions and graph them. This is when they end up looking like, and it says how do the graphs compare? So they have reciprocal slopes. F of x has a slope of 3. G of x has a slope of 1/3. I'm going to switch colors here because I want to draw on this. I'm already using, or there's already a red. So they intersect here, and they also, if you take f of x and just switch the coordinates, you get g of x, and that should be, I mean, that's just from the table. The coordinates were switched, the points were switched, the x's and y's were switched. So for example, there's a point 1, 2 on f of x, 1, 2. And then if we just switch those, and we would get 2, 1 on g of x. And that works for all the points because the table just had the each input and output switch. And then because the x's and y's are switched, I'm trying to draw a straight line. If you reflect f of x over this line, which is the line y equals x, you get g of x. So these functions are called inverse functions. And there's a few things that happen with inverse functions. The inputs and outputs get switched. So that's what we have going on here, 1, 2, and 2, 1. The x's and y's are switched. And also graphically, an inverse function is just a reflection of the original function over this line, y equals x. And that's because if we're saying y equals x, we're like switching the x's and the y's. They're equaling each other. We're just switching under the same thing. Okay, so what is an inverse function? Inverse functions, this is basically summarizing what we've said so far. Inverse functions have the input become the output and the output becomes the input. In other words, x switches with y. Function notation. So notation just means like how we write something. For inverse functions, looks like this. So instead of saying g of x, since g of x was the inverse of f of x, meaning all the x's and y's got switched, and that's how we got g of x, we could have written this. And the way you say that is either f inverse of x is how you read this, or you say the inverse of f of x. That's another way to say it, and that's the way I usually say it, the inverse of f of x. So that's what this means. And then graphically, if you look at the graphs, the inverse function is a reflection over the line y equals x. So because g of x was the inverse of f of x, you could see that on the graph, that you took f of x, and if you just reflected it over this line, then you get g of x. It lands on g of x. Okay, so we're going to talk about another one that has to do with speed and distance. So the following graph shows the function d of s, which is a stopping distance d in meters, needed for a car that is traveling at speed s in meters per second. So we have the speed is the input, and so that's what this is telling us also, this function notation, that speed s is the input. And then distance, the car, so if a car is going a certain speed, the output is how long it takes to stop. So for example, if we look at like 20, if a car is going 20 meters per second, then it's going to need, it looks like about 36 meters in order to stop. All right, so the first question says, what is the domain of the given graph? Domain is the inputs, so it goes from 0 to 30. So 0 to 30, and we're including 0 and 30, and that's why we're using these square brackets. What's the range of the given graph? That's the output values, so 0 to a little above 70, so 0 to 71. Is distance a function of speed? So if it's asking, you've had these questions before, you should have had these questions before, where it's asking if a relationship is a function. And that was where each input value has no more than one output value. And yes, so each input, this should be one word, input has only one output. Evaluate D of 15. So this is function notation, and it's saying plug 15 into the function. So then we look at we don't have the equation to plug it in, so we look at our graph, and we look for where 15 is the input, the speed. And it's asking us to evaluate to figure out what the distance is. So that's right here. And that distance looks like a little past 20. So I'm going to say D of 15 is 21. And that means when you're traveling 15 meters per second, because that was the input, it will take 21 meters to stop. Suppose a car has 40 meters until it needs to be stopped. What is the max speed of travel? Okay, so we're going to read that again. It has 40 meters until it needs to be stopped. That's the stopping distance. It's giving us this output value, 40 meters. What is the max speed of travel? So what's the fastest it can go in order to be able to make that stopping distance? So it's not going too fast and not going to have take too long to stop. So we're just looking at the graph again, and we're figuring out what stopping distance gives us an output of 40. Or initial speed, sorry. What initial speed gives us a stopping distance of 40? So I'm just looking for where the output is 40 on the graph, and then I'm going to go down and figure out that input value. So it looks like about 22. So looking at the output of 40 meters, the input appears to be, and we want units, 22 meters per second. So you couldn't go faster than 22 meters per second, or it's going to take too long to stop, too far. All right, so this is about the same, or based on the same problem. Suppose we wanted to know what speed a car can be traveling for a certain stopping distance. So what speed a car can be traveling for a certain stopping distance. We have the stopping distance, but we want to know what speed it can be traveling at. Create a graph that shows the stopping distance of the car as the input. So now this is the meters, just the distance, and then speed is the output. So what we can do is just take these values, for example, the 15 as the input, the speed, and then 21 as the output, the stopping distance. And this is asking us to just graph stopping distance along the x-axis, the input axis, and then the speed as the output, the y-axis, the output axis. So you can just basically take all those coordinates and then switch the input and the output. And you end up with something like this. So for example, that point I was just saying, 15, 21, is going to switch and become 21, 15. So about 21 and then up to 15. Okay, so what is the domain of the graph? So we're going from here to a little over 70, so about 71, so 0 to 71. And we should notice that was the range of the first graph. So they get switched. And that's because we just basically switched the variables. We switched the input and the output. What is the range of the graph? So it's going from 0 to 30. And that was the domain of the previous graph. Is speed a function of distance? So that's, again, just saying, is there one output for each input or no more than one output for each input? Yes, it is a function. And then evaluate S of 30. So it's saying if you plug in 30 for the distance, then what is the output? So this number in the parentheses is always the input. It's telling you like what to plug in. And then provide like the units. What are we even trying to find? So if we plug 30 in, I'm going to go up and we get a number right here. It's about, it says between 15 and 20, and say about 17. And that's giving us the speed. So I put S of 30 is about 17, which means to be able to stop in 30 meters, you must travel no more than 17 meters per second. So remember, this was the stopping distance. That was 30. In order to stop, have 30 meters to stop, you can't be traveling any more than 17 meters per second. So d of s and s of d are inverse functions because they just switched the inputs and the outputs. So the context of what you were plugging in just switched. Okay, we're going to do one last one and talk about inverse notation, which means just like what this is, this with the -1. That's called inverse notation. Okay, so it's saying given f of x in the table, find f of 4. Let's do that one first. So it's saying if you plug in 4, what is the output? So 4 is here. If you plug in 4, you get 14. So f of 4 is 14. All right, the next one is saying the inverse of f. That's what this little -1 means, the inverse of f of 2. So it's saying take the inverse function. If you plug in 2, what do you get? Well, the inverse function means you switch the inputs and the outputs. So we're actually looking for where the output is 2. What was the input? It was -4. So f, the inverse of f of 2 is -4. Here, let's try that one more time. So the inverse, this last one is saying the inverse of f of 14. So remember, we're looking at the inverse, and that means we're switching the inputs and the outputs. So 14, we're looking at the output. What was the input to give us 14? It was 4. Another way to do it is maybe just recreate a table. So now you're switching all the inputs and outputs in order to get the inverse function. So if I just kind of like draw a new table and switch all these inputs and outputs, when you get to, so the first one, -4, 2, now 2 is the input, -4 is the output. So when you're looking for evaluating the inverse function at 2, you plug in 2, you get -4. So it might help to just kind of like visualize drawing a whole new table and switching the inputs and the outputs. So when you're looking for the inverse, now the output is the input and the input is the output.